Hi guys, so this is next lecture for after I guess we've done up to we have done up to end-to-end PyTorch pipeline. So now today we will be doing some PyTorch interview cheat sheet type of thing. So let's start. So firstly, we will know what's the exact sequence for the PyTorch model training. So it is forward pass, loss computation, backward pass, parameter update, and then gradient descent, which is done by this snippet of code. Now, why loss must be scalar? These are like important questions. So backpropagation requires a single objective value. A vector loss creates multiple optimizations direction. So loss dot backward works directly only for scalar loss. Now, if there will be multiple optimization direction, then loss will get confused to that like to in which direction we need to optimize, or which direction is our we need to move to optimize that direction. So loss get confused. That's why loss must be scalar. Now gradient. Gradient are stores in parameter.grade like w.grade, b.grade. Gradient accumulated by default in PyTorch. Now why optimizer.zero grad is needed? PyTorch accumulates gradient across iterations. All gradients must be cleared before next update, otherwise parameters update becomes incorrect. As I have told all these points to you in previous lectures, just I'm giving you a recap. Now, NN.model, why it is needed? Organize model parameters and forward computation. Does not train the model by itself, and training happens in the loop, not inside the module. Now, what is NN.linear? So, NN.linear takes two arguments, in features and out features. In features is number of input features per sample, and out features is number of output per sample, and batch size is handled automatically. Now, what is tensor set rule? So, if you are giving an input shape, it should be batch size comma feature. If you are giving output shape, it should be batch size comma output feature. Target shape must match out shape for loss computation. As I have told you, the shape should match properly, otherwise it will throw an shape mismatch error. Now, what is dataset and data loader? What's the difference between them? Datasets stores the data, define how to access a simple sample, and must implement length and get item. What is data loader? It's create batches, shuffle data, and iterates over the dataset. As I have told, and I have given you a this demonstration also on this board. Now, this is the code snippet for custom dataset template like class my dataset, and self x, self y, length, then indexing, how you will access is to index. How data loader works internally. So internally what happens? It calls length to know the dataset size. Then it calls get item index to fetch samples, and then group samples into batches, because data loader create batches of the samples, as we have learned before this. Epoch. What is epoch? Epoch is a one full pass over the dataset. And what is iteration? So iteration is one parameter update. So after every batch, parameter get updated. So iterations, how many iteration will be per epoch? The data size upon base size, like dataset size is 100 and the batch size is 20. So how many batches will be there? 5. It means that five iterations will happen in per epoch, and 5 updates will also happen. Now, what is common interview bug? Same mismatch, as I have told you. Forgetting optimizer.zero, use wrong in feature and linear, and loss not scalar. These are like a common pitfalls people actually do wrong during interviews or in coding. What is like now interview one-liners? Dataset defines data access, and data loaders handle batching. This is important line. If an interviewer asks you difference between dataset and data loader, you can say this. Lost must be scalar for back propagation. Gradient accumulate by default in PyTorch, and training logic never changes, only dataset size changes. The next lecture it is on train and validation split and overfitting. So what's the objective of this lesson? In this lesson, we will able to understand why data sets are split into training and validation sets and how overfitting is detected and avoided. Why train and validation split is needed. If a model is trained and evaluated on same data, it may memorize the data instead of learning general pattern. This result in overfitting. Yeah, so this is the main reason. Actually, if you are like I can tell you through a simple analogy or a real world examples. If you are like you have solved 10 questions, 10 mathematical questions, and the same questions come in your exams, then like you have memorized it. You are not means maybe you have solved that 10 question many times so that you get all the steps. And it as after doing it 10 times you have memorized the that solution only, and in exam you get the same question, then it's not actually evaluating you. So what happened like when a different type of question, very different type of question comes, you'll not be able to solve it because you're not aware of flavor or the concept or the pattern inside it. So it's very much necessary that our train split and train data and validation data should be different so that we get an actual validation value, actual evaluation value. Now, what is dataset split? Dataset is typically split in training set, which is like 70 to 80, and validation set like 20 to 30. Other than this, we also have a test set, which we store early only during a split so that we can test our model on test set. This is like unseen data, which model had never seen it. So when model get fully trained, we test it on test set. Now, train and validation split in PyTorch. So we will be importing random split and data loader. Now train size we are taking 80% of the length of dataset, and validation size as length of dataset minus train size, yeah, like which will be 20%. Now we will be splitting it into train dataset and validation dataset. Now train loader we will load in batches to train loaders, and we will also load in batches to validation loader. Now how will be the training loop? So model will start with train model or train. Now model will get trained. Here for x dot bit and y batch, we will be calculating the prediction of x per x value. What will be the prediction? Then we will calculating the loss, then loss backward like what? Yeah, we will be finding the gradient, then optimization, and then we will make the gradient stored value to 0, otherwise it will get accumulated. Now there will be a validation step, which is start with model.eval where with torch no grade. So we start with torch no grade. Why? Because in evaluation step we don't want to find a gradient. We don't need to find a gradient. We are just finding the loss. What is that loss? We don't need to find the gradient. So it will be for x batch, y batch invalid. So why we are doing this? So that it doesn't find gradient. So for access y batch in val loader, y predict is equal to itna and validation loss we can find. So if we write it, then internally the computational graph is not made, so that because every time you do a PyTorch operation, internally computational graph start to mix without, because it's a default case, so we have to write to stop it. Why torch dot no, grade is used? Prevent gradient computation, as I have said you. It will be reduce your memory usage and it will also speed up validation. Now, what is overfitting and why it occurs? Overfitting occurs when training loss decreases, validation loss stops improving or increasing. So training loss is decreasing, but validation loss have like stop decreasing or increasing, or it's not improving. So this is a case of overfitting. Now, never call, these are key rules. Never call lost or backward validation, as there we don't want to find gradient. Never update parameter during validation, and validation is only for evaluation, not for any update. And now interview takeaways are training data update. The model validation is just measure the generalization, how generalizes your model. Torch dot is mandatory for validation. The next lesson we will be learning about early stopping and regularization. Now, this objective of this lesson is to understand how overfitting can be controlled using early stopping and L2 regularization. So, why overfitting occurs? Overfitting occurs when a model learns noise or memorized training data, resulting in low training loss but higher validation loss. Yeah, so early stopping, early stopping halts training when validation performance stops improving. So in like previous case, we are not stopping our model. We let it we let it be in its situation. We don't uh, bother about it, like how what happened to the model, is loss decreasing or not. We just given the epoch and left it in its situation. Excuse me. So after that, what happened? So the model starts to learn noisy data, and then the validation loss is more, there is a very big gap, like more than 10% gap between training loss and validation loss. So this is the situation where overfitting must be happen with your model. So you must look at the validation loss and training loss gap, so that it can you can improve, and uh, you can if you will be knowing about the error, what is actually happening, if you have a knowledge of overfitting, then you can use it to overcome overfitting by using early stopping and regularizations. So what is early stopping? Early stopping halts training when validation performance stops improving. So what is the key idea behind it? Monitor validation loss and stop training when validation loss does not improve for several epochs. So why validation loss is used? Training loss is computed on seen data, is usually decreases monotonically. Validation loss is computed on unseen data, which reflects the actual generalization of your model. So how the early stopping logic is implemented. So we start with a variable, assigning its infinity value and a counter equals to 0. For each epoch, we train a model, compute its validation loss. If validation loss improve, we update it to as a best loss and reset a counter. Else, we will be incrementing the counter. If the counter value it is exceeds our patience, then we stop the training. Now, what is actually happening here? Like counter value, every time you are incrementing a counter, because the validation loss is not improving. So every time when you increment a counter, if the time, look at the time when it exceeds patience, we stop our training there only. Now, this is the actual code where you can see patience we are assigning 3 and counter as 0. We are taking epochs range 100, and well, model actual training of the model happening here. Then model evaluation is happening every time. So why we're now here? We are calculating loss, and then we are incrementing it validation loss variables with loss items every after every loop. So why? So because we will be checking it on whole epoch now, because we are for one epoch uh, after see here, like when this when this step runs for train for one epoch you have seen whole data. Okay, so after seeing a whole data, we come to model evaluation inside that epoch only, and for that epoch in validation loader also we have separated it into some batches. So we need to have loss of each batches uh, sum up, and that sum up will be the actual loss for whole validation data. Now we will be dividing it with the length of validation loader, which will actually tell you the validation loss, because this sum up value will be, yeah, so this sum up value, we can't use it. We have to divide it by n to get an actual value with respect to each samples, like what we do in MSc also, or RMSc. So here the value, if that value is less than best validation loss, then yeah, base validation loss will be equal to that validation loss, and counter will become 0. But if it is not, if it is greater than validation loss, uh, so if validation loss is greater than best validation loss, the counter will get increased, and when it exceeds our patience, then it's break. Now, what is regularization? So this is different techniques to overcome, solve overfitting. So it is also known as L2 regularization or weight decay. So here in regularization discourages large weight, which reduces model complexity and improves generalization. So whenever there is like large weight, it's try to discourage it. We don't want large weight because large weight actually increase model complexity. So we have to reduce it. We do L2 regularization, and it also improve our generalization because properly the model will be able to learn the data here. So what happened, how we start with how we calculate the loss in this case. So loss will be loss of data plus lambda times w square. So doing w square, if your weight is large and you are doing this square, then it will become more larger, like it will become more large than its actual weight. So it is like highly penalizing the model. So model will be like trying to learn better, reduce weight so that this loss value get decreased. So this is the actual intuition behind doing this. Now weight decay in PyTorch, how we do it. In PyTorch, L2 regularization is applied using weight decay. You can optimizer.torch.optim.sgd, that's actual this our previous script. Then model parameters, linear learning rate, we add one extra argument, that is weight decay equals to 1e to the 1e to the power 1e minus 4. So this is 10 to the power minus 4 time. So weight decay equals to this. Now when you add this is lambda value, this is the lambda value. Yeah, so this will now like this will now work with this mathematical form. Now what weight decay does? Penalizes large weight, encourages simpler model, and does not modify data. Now comparison of a technique. Method train and validation is split. Measure generalization. Early stopping decide when to stop training, and weight decay control weight magnitude. Now, some interview takeaways are early stopping uses validation loss, not training loss. Weight decay reduces model complexity, and both technique helps prevent overfitting. Now we will be learning. Now we will be learning rate and schedulers. So the objective of this lesson is to understand the role of learning rate in model training and how learning rate schedulers improve convergence and generalization. So I guess I have told you about learning rate, why a learning rate should have a particular correct value, not more like not very big, not very small. So and this is like how we weights get updated. I have also told you about this. This eta is actually the learning rate and this is the gradient. Now eta is the learning rate, yes. Now effects of learning rate. If learning rate too large, training become unstable, loss oscillate or diverges, model overshoots the minima. Yeah, because it will be rate will be large and then it will not come slowly or not get converged. It will be overshooting here and there in the convergence uh, in that loss graph. Now learning rate too small, training is very small models that you are not to learn and takes many epoch to converge. It's like you are taking very small steps. Now what will be the good learning rate? A smooth loss decrease and a stable convergence. Why learning rate schedulers are needed? During training, early stage required, like take a situation like you are updating your model parameters. Now you have started from here and you are to converge to minima. Now, if you will from starting only, if you will take very small steps, it will take very long time. And if from starting you are taking very large step, it may happen like you overshoot. So what we will be doing from starting, we will be taking large steps, but when we will be getting near to minima, we will start to take smaller steps so that we don't overshoot it also, and our computational time is also like minimized. So early stages require large learning rate because we are doing exploration, but in later stages we'll make a smaller learning rate because we are doing fine tuning. So learning rate schedulers automatically adjust the learning rate during learning. So how you will be doing it through code. So there are different type of learning rate schedulers. First one is step LR, which reduces learning rate after a fixed number of epoch. So you can call it like this: scheduler equals to torch optim LR scheduler dot step LR. and its parameters optimizer, step size, and gamma. Gamma is actually the step. Like every 10 epoch, the learning rate is multiplied by 0.1. So after every 10 epoch, it's it is decreases your learning rate so that you go slowly near the minima. Okay. Now other one is reduce LR on plateau, reduce learning rate when validation stops improving. So why you are reducing learning rate when validation stops improving? Because this is like this, uh, it is like a bowl that convergence or a loss curve where we converge to minima. It is like a bowl. So when you are near to base, your loss will improve, like loss improvement will be very minimal. So it gives you an intuition that you are getting near to minima. That's why we start to decrease our learning rate, uh, like more we start to reduce our learning rate there more than when we are in the upside of the bowl. So we can call that scheduler in this way, torch optimal LR scheduler. There you have written a step LR. Here you will write reduce LR on plateau. And here optimizer mode will be minimum, patience is 2 and factor is 0.5. So its meaning is if validation loss does not decrease for 2 epochs, the learning rate is reduced by half. This factor is actually half and this is patience. So after 2 epochs are not decreasing, it means you are near to minima. So it decreases learning rate. Now, how we'll be using it in training loop? So you will be train, you will be validating, and then you will apply schedulers. That is step. Train validations and then scheduler for both. Now, training loss versus validation loss. Training loss is used to compute gradient, where validation loss is used for decision making. Validation loss reflects generalization on unseen data. Why reduce learning rate on validation plateau? Yeah, as I have told you, if you are near to minima, it will start like validation will be improving very minimally, like very minimal improvement will be there. So that's why it gives you an intuition actually. Comparison of schedulers. Step LR, epoch count, reduce LR at plateau, works on validation loss. Relationship with early stopping. Learning rate scheduler adjusts how fast learning happens. Early stopping decides when to stop training. Yes, because learning rates actually adjust your fast learning, like adjust your pace of learning. And early stopping decide when to stop. Both helps prevent overfitting. Learning rate controls convergence, speed, and stability. Yes, and reduce alarm rate uses validation loss, not training loss. Okay, decreasing learning rates help fine tune near minima, and training loss is season using validation loss. Now, this is like lesson 14. We will be learning about different type of optimizers like stochastic gradient descent and Adams. So the objective of this selection is to understand how different optimizer update model parameter and when to use SGD and when to use Adam. So what is an optimizer? An optimizer update model parameter using gradient computed due to backpropagation. This is a technique to update your parameter. Now, as we are using SGD in all the codes we have studied before, SGD use same learning rate for all parameters. Yes, same learning rate. 0.0 for weight also for bias also. Then there is another type of like we can have other parameters also, arguments also. So SGD will, when there is momentum also given 0.9. So momentum actually accelerate SGD by accumulating past gradients. So it accumulate your past gradients so that the speed become faster. Now third is Adams optimizer. So Adams adapt the learning rate for each parameter based on gradient statistic. So it does not use fixed learning rate. It's update, like it's adapt the learning rate differently for different parameters, for weight different, for bias different. Now what will be the property? Learning rate fixed and Adams have adaptive per parameter. Convergence speed will be slower and will faster because you are actually adapting the learning rate, so not fixing it. Turn tuning effect more and less, generalization often better, sometimes worse. Why Adams converges faster? Adams uses adaptive learning rates, allowing faster progress in direction with consistent gradient and smaller steps when gradient are noisy. So this is actually the advantage of Adams, which allows to converge faster. These are important questions which interviewer actually ask in interview. So be prepared with this. Why ZD generalizes better? SGD uniform and slower updates help the model converge to flatter minima, which usually generalizes better to unseen. Here, actually, we don't generalize, or that's why it sometimes get worse. Like because we are taking a very large step in, very large learning rate in some for some parameter, and very small in some parameter. For small, yeah, you can generalize, but you are taking very large, it may happen that you are not able to generalize the data. Yeah, now when to use what? For Adams, for quick prototyping and early training, and SGD for fine-tuning and better generalization. The interview takeaways: Adam converges faster due to adaptive learning rates. SGD often generalizes better due to stable updates, and optimization choices depend on training stage and training problem. Yeah, now this is the mini test question with some solutions. Like you, it is, yeah, it have 9 questions. Let's do it. Why is normalization important? I've told you in earlier lectures. So normalization brings features to a similar scale, stabilizing gradients and improving convergence and generalization. What is the difference between training loss and validation loss? Training loss update parameter using gradient, while validation loss evaluates performance against data without updating parameter. Why we use model evolve and torch no grade? Model evolve sets correct layer behavior and torch no grade disables the gradient computation during validation. What problem does early stops solve? Early stops prevent overfitting by stop training when validation loss stops improving. Effect of learning rate too large and too small, too large than overshooting, too small and slow learning. Why reduce LR when validation loss plateau? So because the model is near minima and needs smaller, yeah. So why we reduce LR? Because if it is near to validation, sorry, it will be near to minima, then validation loss starts to improve very minimally or no, or then there is no improvement. So we give intuition that we are near to minima. Why does Adam converges faster and SGD generalize better? Adam adopts learning rate per parameter while SGD slower uniform updates help reach flatter minima and better generalization, hence better generalization. Why no backward pass during validation? Because validation is used for evaluation, not for learning. Training loss decreases but validation loss increases. What to do? Apply early stopping and do regularization. As your training loss is decreasing but your validation loss is increasing, and this is a case of overfitting. So we need to apply a early stopping and L2 regularization to remove that problem, overcome that problem. Yeah, so we are complete with basics of like PyTorch. We have complete this part. Now, maybe after this, I will be moving towards some advanced topics. This will be the, like that will be phase two. This is phase one. Now we will be moving to phase two. Maybe before that, I have some lessons to give you. So in next lecture, we will be dealing with that part. Yeah. So till then, bye bye. And if you have any doubt, if you want anything from me, like if you want more lectures on some topics, or if you want that I should start some new subjects, new topic, you please you comment down. Yeah. Thank you.